Hello, and welcome to this video. I'm hoping to keep this under 30 minutes. I'm going to try to give you guys a crash course behind what kinematics are, the different kind of variables involved, and where do these weird equations come from. And let's just start with something really intuitive. So things like, we're going to say, so we're going to use x, v, and a, right? This is position, typically measured in meters. This is what we call velocity. Meters per second are the units. Acceleration, these are the letters we're going to use in our kinematic equations to represent those quantities. So we got meters, meters per second squared. These are what are known as SI units, which I believe stands for Standard International Units. These are the units that everybody across the entire world uses to actually do physics. So you don't necessarily want to be using miles or hours and miles per hour and that sort of thing. You want to stick with meters and seconds. That's what all of Newtonian physics is sort of grounded in, and if you change the units, a lot of the equations you're going to have to use will also have to adjust, and a lot of our constants and so on. So use meters, use seconds. But what actually are these things? So to kind of elaborate a little bit more on velocity specifically, you want to think of velocity as speed with direction. Because if you're talking to a friend and you said, hey, I went 60 miles per hour, it's implied that you're talking about some sort of positive quantity, whereas velocity can be positive or negative. And it all depends on the direction of motion, right? So if I have a car and I'm going this way, we might say that this is a positive velocity, right? If my coordinate system is listed this way, let's say this is like my ruler for position, right? So this would be the positive end and this would be the negative end. I could also have a car going this way. Maybe it's even going the same speed, right? Maybe we call this V1 for car 1. This is car 2. Maybe it's even going the same speed, but it's going in the opposite direction. We would say this is a negative velocity, right? Less than 0. So speed and direction, right? This is super important because later on we're going to be modeling velocity as a vector, and those are the two things you need for vectors: size and direction. Speed is like the size of the vector. Don't worry about vectors now. We'll get to that later, right? So what is acceleration? Acceleration has a similar relationship to velocity as velocity does to position. So let me mathematically lay it out for y'all. We know what position is, obviously. It's just basically where you are on the coordinate axis that we're looking at, right? So namely here. Velocity, maybe the very first thing you learn is that velocity is the change in position over change in time. And yes, keep in mind, right, this could be positive or negative. So change in position, the negative result of velocity kind of comes from this right here. Another way to sort of say change in position, we typically, it's kind of a mouthful, we just say displacement. Displacement. Your displacement can be positive or negative. So just to throw some examples up here, right? Let's say this is 0, and that's, let's see, 2, 3, 4, 5, right? Like I could have, maybe I'm here at 1 second, and I'm here, let's say this is 1 second, and I'm here at 2 seconds. I could actually draw my displacement as an arrow, sort of starting at my initial position and ending at my final position, right? And if I walked backwards, right, let's say I walk backwards a little bit and I'm here at 3 seconds, change color a little bit, I could draw my displacement vector from 2 seconds to 3 seconds. It would be an arrow pointing the other way, right? So this is what I'm talking about when I say that displacement can be negative, right? If this is the positive and that's the negative, that would be a negative displacement vector. Over here, this would be a positive one, right? So basically, are you walking forward? Are you walking backward? If you're walking backward, your displacement is negative. Again, it's all based on the coordinate system you set up. But anyway, this right here is the mathematical relationship of velocity to position. And what you might notice right here is this looks an awful lot like rise over run, sort of from mathematics. And if you know what that is conceptually on a graph, we also have a graphical visual connection between position and velocity. So here's what I mean by that. Let me change this back to blue. If I were to make a graph of some kind of 1D motion, and we'll just say that this is a constant velocity situation, but let's say my object is traveling at some sort of constant speed. Think about, this is 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds. Let's say this is like 2, 4, 6, 8, 10. And let's say I'm traveling 2 meters per second. What does that mean? That means at 1 second, I'm at 2 meters. I'm at the 2 meter mark. At 2 seconds, I'm at the 4 meter mark. At 3 seconds, I'm at the 6 meter mark. And so on, right? It turns into a line. Right? Now, that's considering that this is my initial position, right? Which we're going to denote as x with a little 0 in the subscript, right? So if I had a different position, I could end up with a different graph. What if I already started at the 6 meter mark, right? Then I would increase 2 meters each second, and I would end up maybe with a graph looking like this, right? Notice how that's a parallel line. And what do these things have in common? They have the slope in common, right? So what's really cool about the connection here is that, let's do a different color, that the slope, specifically the slope of the tangent lines to our graphs, in case these get all curvy on us, these are all your velocity, right? So the velocity equals the slope on an x versus t graph, right? Specifically this one. It's not going to be valid for other graphs, right? And it's because of this mathematical relationship there, right? So that's actually pretty cool. What's really neat, though, is we can also use this position versus time graph to get the corresponding velocity versus time graph, right? So I could also make a graph that corresponds to the same kind of motion, except now I can graph the velocity versus the time. And in this case, the velocity is constant, right? So maybe I go up by 1 unit each time, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8. Let's keep the scaling pretty much the same. What would this graph look like? It would be a horizontal line that goes through 2 on the y-axis. Right. So these two graphs both correspond to the same motion. Same exact motion, same object going at 2 meters per second. They're just representing different aspects of that motion, right? Either position or the velocity. And that's keeping it really simple with constant velocity situations, right? What's really neat, one other connection too, right? So notice how we said that the velocity was 2 meters per second. Now, if you really think about what that actually is, it's kind of a weird thing. Meters per second. What actually is that? Because we don't have rulers with meters per second on it, nor do we have stopwatches with meters per second. Yes, you can calculate it, but what actually is it? it means that every second, every second you travel 2 meters. So it's just a really useful idea to kind of keep track of how much displacement we're covering in a certain amount of time. And so we can extend it and say, well, if I traveled half a second, how far would I go? Well, you would go 1 meter. And what's really neat is the area under this velocity versus time graph exactly corresponds to the displacement. So let's say I found the area from here to here. Right? I'm claiming that this is the change in x from specifically 2 seconds to 5 seconds. Right? The displacement from 2 seconds to 5 seconds. And let's actually calculate what that is. Right? So the height of that rectangle is 2, and the base is 5 minus 2 is 3. Right? So we have a calculation of 3 seconds times the height is 2 meters per second. And what's really cool is notice how those units perfectly work with each other. Those seconds cancel. What are we left with? Exactly 6 units of meters. So sure enough, even the units work out in this calculation, right? So what does that correspond to up here on this graph, right? So my position on this graph was at 4, right, over here. And when I get to 5, my position was at 10. So the displacement on this graph looks like the change in height. This was your change in x, specifically from 2 seconds to 5 seconds. Right? So now you can see the slope on a position versus time is your velocity, and then the change in heights, those are your displacements, right? And then down here on a velocity versus time graph, you have the area under the graph is your displacement. And what we're also going to talk about next is what does the slope on this graph represent? But we might want to make our situation a little bit more interesting. So let's talk about acceleration here. Let's see, do I already have the equation up there? No, I don't. All right, so acceleration mathematically is change in velocity over change in time. Notice what happens with the units, right? So I have a meters per second quantity divided by a quantity of seconds, and that gives you that quantity meters per second squared. This one is even more harder to wrap your mind around. We're very used to talking about speed colloquially, so it makes a lot more sense to us. But acceleration is kind of a weird concept. And I saw on the summer assignment, this is something people kind of get tripped up on. What actually is acceleration? All you really need to know is basically this mathematical relationship, and you also need to sort of view it as sort of like a rate of change of velocity. Again, still kind of a hard concept to wrap your mind around, but it has the same kind of relationship to velocity as velocity does to displacement, right? You can see mathematically why that's the case, right? So you want to think in similar terms. So let's actually start off with an object with some kind of acceleration, some kind of constant acceleration. So I'm going to give it a very simple graph. 5, 6, 7, 8, 9, 10. All right, cool. I'm just going to give it 1 meters per second squared for some, indefinite amount of time, right? So this is my acceleration versus time graph. Right. So what can we do with this thing? Right, so think about the connection between velocity and position, how I had this horizontal line here and it translated to this sort of slanted line there. There's the exact same relationship between a constant acceleration and velocity, right? So I'm I'm going to make it a little bit more complicated in this case, though, because what if the object is already in motion, right? And I'm not going to be too specific with the tick marks here. But, let's suppose the object was already going at 2 meters per second, right? So my graph actually already starts here. And we have an acceleration of 1 meters per second squared. So what does my velocity versus time graph look like? Oops, forgot to do these tick marks here. It's going to be a line sort of going at this slant. What does the slope need to be? It needs to be exactly 1, right? Because over in this case, the slope of this graph, these slopes right here represent your acceleration, right? A constant acceleration of 1. Now this is the fun part. On our velocity versus time graph, not only can we get the acceleration, we can also get the displacement, right? So we have an acceleration of 1. If I wanted to find, let's say the displacement from 2 to 4, then what I could do is I could just find this area here. This would be my, this would be my displacement, this area. It's also important to point out that area can have sign to it. So we say it's a signed area, because if your graph, you'll see examples like this later. When your graph goes below, let's say this is some velocity versus time graph, you can have situations where over here, you have a displacement that's positive, but then once it goes underneath, all of a sudden your displacement is negative. And you can even have situations where these two areas cancel each other out. So that's something to keep in mind. It's not always going to be positive area. Just make sure you're thinking about the height in the right way. Okay. And you know what? Let me make this example maybe a little bit simpler. Let's just find the full displacement from 0 to 4, right? So, does anyone remember the area formula for a trapezoid? Really good question here, right? Keep in mind that 2 is my starting velocity, right? We call that V0 or V0. So the area of a trapezoid, in case you forgot, is 1/2. Now, 1/2, it's kind of weird because our trapezoid is sort of sideways here. So you want to think of this as like the height. We want to think of this as like base 2, and this right here is my base 1. Because the formula for the trapezoid is 1/2 base 1 plus base 2 times h. There's other formats for the formula. That's just the way I'm going to use it. All right, so if I plug those things in general, I'm not going to use the numbers here. My base 1 is actually equal to whatever starting velocity I had, so namely v0. My height is the amount of time that has passed. So in general, this is just t, right? And by the way, I'm calculating displacement, right? Just by finding the area of the trapezoid. We know that the area under velocity versus time graph is your displacement. We saw that before. Now, what is B2? Right? Because it has sort of, it has B1 in it and then plus some extra height. So how do we get that extra height? Well, what we do is we follow, so if I have a triangle in general, right, and this is 3, and let's say I know that the slope is equal to 2, and let's make this interesting here. Let's say 0, 1, 2, 3. So let's say this point is already at a height of 3. How do I find where the next point is? Well, I would take 3 and I would add the slope times how much horizontal distance I covered, which would be 3 in this case. Let me choose a different number. Let's just say 4, right? So just so you're not confused about which numbers go where, right? You would take the slope times the amount of horizontal distance we covered, right? So we're calling this horizontal distance t. Remember, I put it over here. And so what is B2? B2 is going to be my starting velocity plus the slope of my graph, which what did we say it was? Acceleration. So acceleration. And then times horizontal, sort of the horizontal distance we traveled, which was t. So look at this. This is going to be one of our big kinematics we're going to use a ton here. Right, so let me get rid of all this stuff. Change in x. I'm going to go ahead and change the way we're going to write this quantity here. Change in x is literally, mathematically, just whatever final position you have, xf, minus the initial position, x naught or x0. Over here, I'm going to simplify some stuff inside here. So we have 1/2 2 times v naught plus a times t in parentheses, and then times t again. All right, so let's distribute this t in here. We could also go ahead and just distribute the 1/2 as well. All right, let's just do both of those steps at once to save time. All right, so 2 times 1/2, those sort of cancel out, and then I have v naught times t. I should end up with v naught t. All right. The next one, the 1/2 doesn't cancel with anything, so I have plus 1/2. The a stays the same, but now I have t times t. Check that out, that's t squared. And if I just add the x naught over, I get that xf, final position equals initial position, plus v naught times t plus 1/2 at squared. This right here is one of your main kinematics you're going to be using a lot. A lot, yeah. So this is for situations in which we only have a constant acceleration. What's great about deriving this kinematic first is that we can get a lot of other kinematics pretty quickly after, right? So let's say, suppose a equals 0. What does this mean? Well, this means that my final position is my initial position plus initial velocity times t plus 1/2 times 0 times t squared. And when that happens, this whole term turns into 0, it goes away, and we get another kinematic that goes on your sheet somewhere. Final position equals initial position plus, in this case, since acceleration is 0, the velocity is constant. So instead of saying v naught like we did up there, we could just say v because it's not changing at all. And so this right here is another kinematic. In fact, we could have derived that kinematic if we went all the way back up here, right? Because essentially what we have here is v equals xf minus x naught over t. And you could solve for the final position, right? Get it isolated by multiplying both sides by t. So we actually could have derived that from the very beginning. We could do something very similar over here too, right? So acceleration equals change in velocity. That's the same thing as final velocity minus initial velocity over however much time has passed. And if sure enough, if we rearrange this for final velocity, we get a kinematic that looks pretty darn similar, except it's focused more on the velocity and acceleration of the object. All right, but you notice there are some very telling similarities between those two because they have similar mathematical relationships to each other. So that's really cool. There's sort of one other thing I need to go over here, and that's the kinematic that doesn't have time. So there's a lot of examples in physics where an object is sort of dropped and you're given, let's say, the change in I guess, just think of this as a displacement. This is vertical displacement, right? And let's say you have the initial velocity, you have the acceleration, you have the final velocity, right? So whenever the ball is here, it has some sort of final velocity, but you don't know how long it took for the object to fall. There's a case in which we can use a kinematic that doesn't have t in it whatsoever, right? Because in this case, this kinematic's not going to work, this kinematic's not going to help us, that's not going to help us either. We need one more kinematic, one that doesn't involve time. And for this derivation, we have to just rely on math. There might be a more visual way to kind of see this. I have yet to find it, but let me show you all how I sort of derive it myself. So what I do is I take, let's see, what's the best way to do this here? I sort of rearrange this equation here. So if I multiply both sides by t and divide both sides by a, I get that t equals v final minus v initial over a. So what we can do is we can make a quick substitution. So this is my substitution into this kinematic right here, right? So I'm going to plug this substitution in for every single time I see t. I'm also going to, let's see, I'm going to use delta x instead of xf minus x0. I'm also going to use delta v instead of this subtraction here. I'm just going to try to keep things as simple looking as possible, right? So let's see. So I'm actually going to use this version of the substitution, and I'm substituting it into that big kinematic we found earlier, right? So we're putting it into this thing. All right, so what does this become? Okay, delta x equals v naught times, this would be change in v over a, right? Substituting in for the t. Now I'm going to plug it in over here as well, right? So t squared. Let's see, is that the best way to substitute in? You know what? Actually, change my mind. I'm going to use maybe this format for the kinematic instead. There's actually something that works really nicely inside those parentheses. So let me change this a little bit. Let me change it one more time. So I'm going to put in the substitution into this version. Right? They're both mathematically the same thing. All right, delta x equals 1/2 times 2v naught plus a times delta v over a. So hopefully you can see why I did that, right? Makes my life a lot easier if I do it into that version, because I get these nice little cancellations here. That's beautiful. And keep in mind, this is v final minus v initial. So once those a's cancel, this v initial was going to cancel with one of these. So again, that's why I wanted to do this version here. So I have delta x equals 1/2. Looks like I'm left with v final plus v initial. And then over here, I have v final minus v initial over a. Let me maybe rewrite this a little bit so it's easier to see what's going on. So I'm going to rewrite it this way. I'm going to put the a in that first fraction. And now, hopefully you can kind of see that I have a difference of 2 squares there, right? So maybe what I do is I'm going to multiply all this out, and I'm also going to multiply both sides by 2a, right? So that way that this and this cancel. And what do we have? 2a delta x equals, it's going to be v final squared minus v initial squared. It's difference of two squares formula. Nothing crazy here. And if you rearrange this around, do some math, we get our final kinematic. Vf squared equals v0 squared plus 2a delta x. That right there is your final kinematic. And notice how there is no time involved. And that is awesome because there are a lot of cases where you are not given the amount of time, right? You're only given the displacement, maybe the acceleration, initial velocity. You're trying to find the final velocity. Or maybe you're trying to find the displacement and you're given the final velocity. You know, who knows? They could change up the question in all sorts of ways, but the point is there's a lot of situations in which you don't have time, but you don't need time, right? So these are the main kinematics, right? So this one you're going to use a ton if you have time, meaning like they give you the amount of time the object has been moving. These are super useful when you're just trying to find simple other missing quantities like position and final velocity. And then this is the one you want to use if you read the problem and you realize that you have not been given time from the problem. Okay, so those are the main derivations. Those are pretty much the 4 or 5 kinematics that I believe show up on your sheet. Actually, looks like maybe only 3 of those show up. So there's a spot, let me do this in green. There's a spot for this one, it looks like. There's a spot for this one. That one's super important. And there's a spot for, yeah, it looks like this one, although it has it written a little bit differently if you look online at the actual sheet. The point is these are the correct equations. You're going to have to be kind of comfortable using these. But you also need to understand the concepts behind acceleration, velocity. And to circle back to these graphs, right? All right, now that we know this relationship, right, what does the graph in a constant acceleration case look like for an object? So think about it, right? Think about this equation here. We have time squared. So what does that mean our graph looks like? It's going to be some kind of parabola, right? It could look maybe something like this. It could look something like that. It could even, you know, if you got some kind of falling object, you could throw an object up and it comes down. But the point is, position versus time, if A is not equal to 0, is going to be some kind of parabola, upward or downward opening, right? And we can see that in the equation itself, right? The highest power on T is 2, so it's some kind of quadratic. The only other thing that I need to show you guys before I end this video is motion diagrams. These don't show up a lot. I wanted to show you all the equations first because those show up the most. Motion diagrams are just something that it's nice to know them. They make a lot of intuitive sense. The point is, a motion diagram is kind of like a snapshot at equal time intervals for an object in motion. All right, so what does that mean? It means we draw a bunch of dots that are a certain amount of seconds apart. That doesn't mean, though, that they're equal distances apart. So let's just show you a few examples. If I have some kind of constant velocity situation, think about it, right? If I had some kind of object that was moving exactly 2 meters per second to the right, let's say velocity is 2 meters per second to the right, you know, we would represent that with an arrow. That means the object is covering 2 meters every second. So the motion diagram for that object would look something like this, right? And we would want to draw those velocity vectors. The vectors for velocity don't necessarily need to reach the next dot. Now the displacement vectors would, right? So if these are velocity vectors right here, these are velocity vectors, we would say that these are the corresponding displacement vectors, right? That is literally the actual distance the dot has traveled. And so constant velocity situations are pretty boring when it comes to motion diagrams. We could also have them going the other way too, right? So if we had the dot going, I don't know, let's make it interesting, -3 meters per second. It probably, the arrows would be a little bit longer than the ones above, and they'd be going to the left, right? For some sort of constant acceleration situations, let's say our acceleration was 1 meter per second squared, something like that. What would we expect the dots to do? Right, so let's say the object is initially, I'll put V naught is initially 0 meters per second, and I start here. Well, after 1 second, my velocity should be 1 meters per second. So, let's say, it's hard to gauge how much displacement it should have traveled because its velocity is changing at every single moment in time, right? And this is some sort of quadratic relationship, right, according to that equation there. But there are some things we could say. So let's say that it travels this displacement after 1 second. This is 0 seconds here. Where should I draw the next dot? And again, think back to that mathematical relationship here, namely that this is a quadratic, right? It's according to time squared. That would mean that if I traveled 1 unit after 1 second, I should have traveled a total of 4 units by 2 seconds, right? And then at 3 seconds, I should have traveled a total of 9 units. So this would be at 3 seconds. And then for the next one, I should have traveled a total of 16. So 10, 11, 12, 13, 14, 15, 16. Right? And we can also sort of try to scale the velocity vectors accordingly, right? So our velocity should be constantly increasing every second. It should be gaining 1 more unit each second. So let's say my velocity vector takes up half of that distance there, right? For the next moment in time, at 1 second, it should be 2 times as big. And then at 2 seconds, it should be 3 times as big. And then at the next second, it should be 4 times as big. And then 5 times as big. Right? So motion diagrams are a little bit more interesting with acceleration, right? There's also situations in which you could have acceleration and velocity go opposite directions, and you can see your dots get closer together at the end of your motion diagram. So, I could have a situation where I'm like this, and then 1, 2, 3, 4, 5, 3, 4, 5. I'm here. Then my velocity gets a little bit smaller. 1, 2, 3. Then my velocity gets a little smaller. Let's see, 1. So this would be a case where my acceleration might be -1 meters per second squared, but my initial velocity was, let's say this was, I want to say 4 meters per second maybe. I'm kind of guessing here, I'm running out of steam. But the point is, if your acceleration and your velocity are in opposite directions, right? So let's say velocity is positive, acceleration is negative, or if you have velocity is negative, acceleration is positive, these are cases in which your object is slowing down. Right? In whatever direction it's going, doesn't really matter. The point is the acceleration is sort of working against your velocity. Whereas if my velocity and acceleration have the same sign, doesn't matter if they're both positive, both negative, that's a case in which an object is speeding up. Right? I mean, just think about mathematically. If acceleration is +1, velocity is +2, you're adding numbers, you're adding, I think I said acceleration was +1, you're adding 1 unit to your velocity each time, and the size of that number is getting bigger. So that only happens if they're both sort of pointing in the same direction. Right? So this case up here was a case in which my acceleration vector might be pointing this way. This case over here, the acceleration vector was pointing in the opposite direction of my velocity vectors. So I think I've gone on way too long now. I'll go ahead and probably upload these notes into the drive as well, so you guys have them. And we'll, of course, see ways of how to apply these equations in class. We're going to do a bunch of practice problems. We're going to see some more connections. But it's really important you understand these concepts. The graphical connections are heavily emphasized, right? So what is the area under a graph is a really big question. If they just give you any graph, does the area actually mean anything, right? And what does it mean if it does, right? Because if you look up here, you know, this area under this graph doesn't mean a single thing, right? You can even think about the units multiplying. This is meters times seconds. What is that? I don't know. I don't know what that represents at all. It's basically useless, right? Whereas the area under a velocity versus time graph does actually tell you something. It tells you the displacement, right? And of course, the slope on this graph would give you acceleration, right? Acceleration. And that applies to more general scenarios too, right? So if you have a more curvy graph, which you can't really do much calculations on, but let's say your velocity versus time graph looked like that. To find the acceleration at different points, you would draw little tangent lines, right? The lines that are just touching the graph at exactly one point. The slopes of those lines are all your instantaneous accelerations at different points, right? Because this is like the speed of a car that's sort of increasing and then decreasing and then increasing again. Its acceleration, net acceleration, is changing. And of course, you would still have that the area underneath the graph is still the displacement. So concepts like that are heavily emphasized on the AP test. And of course, there will be many situations in which to use these kinematic equations. These are the ones that you want to have committed to memory. And eventually, if you do enough practice, they'll come a lot quicker and a lot more naturally to you. Right. Motion diagrams appear a fair bit as well, so I wanted to pepper those in. Anyway, went on way too long. Hope you guys have a great rest of your day. See you later.